Welcome to today's paper reading. Today's paper is titled, Back to Basics, Revisiting Reinforced Style Optimization for Learning from Human Feedback in LLMs. This paper was published on the AR14 preprint by Arash Ahmadian and colleagues from Cohere for AI. The abstract highlights the importance of AI alignment, specifically through reinforcement learning from human feedback, RLHF, in the development of high-performance large language models, LLMs. Proximal Policy Optimization (PPO) is currently considered the standard method for the RL component of RLHF, but it comes with significant computational costs and requires careful hyperparameter tuning. The authors argue that the principles driving PPO's development are less relevant in the context of RLHF and propose the use of simpler, less computationally expensive methods that can maintain or even enhance performance. They revisit the concept of alignment from human preferences within the framework of RL, emphasizing simplicity as a key principle. Their findings indicate that many components of PPO are unnecessary in RLHF and that simpler reinforced style optimization variants can outperform both PPO and newer RL-free methods like DPO and RAFT. This research suggests that adapting to the specific characteristics of LLM alignment can enable effective online RL optimization at a lower cost. The introduction of this paper discusses the current state of large language models, LLMs, which are pre-trained on vast amounts of text data. These models often contain complex preferences, relations, and intentions that may not align with human preferences. The research community is interested in how to align these models with human preferences. Despite significant research efforts, there is no consensus on the best approach to achieve this alignment. Reinforcement learning from human feedback, RLHF, is one of the most widely regarded methods, but it comes with challenges such as high computational cost and optimization difficulties. Recent works have proposed RL-free methods and iterative fine-tuning approaches, but these do not address the question of whether a simpler solution within the RL paradigm exists. The paper aims to explore whether it is possible to avoid the computational and optimization complexity of PPO while maintaining performance. Figure 1 illustrates the training reward curves for Proximal Policy Optimization (PPO) on Llama 7B models using the HH dataset in a reinforcement learning from human feedback (RLHF) environment. On the left, it shows that a higher emphasis on variance reduction at the cost of bias, low lambda, performs worse compared to strategies that introduce less bias but forego variance reduction, high lambda. The vanilla policy gradient with lambda equals 1.0, which has the highest variance but no bias and uses the full trajectory reward in each update, performs the best. On the right, it demonstrates that PPO is unnecessarily complicated for RLHF, as removing various augmentations of PPO, such as clipping and loss normalization, does not degrade performance. The original RLHF pipeline for large language models, LLMs, proposed by Ziegler et al., 2020, is divided into three main stages. The first stage is the supervised fine-tuning, SFT, stage, where a pre-trained language model is fine-tuned using a dataset of instruction prompts and human-written completions. The second stage involves training a reward model as a binary classifier, which is used to provide feedback in the third stage, the reinforcement learning, RL stage. In the RL stage, techniques like Proximal Policy Optimization, PPO, are used to optimize the policy with a token-level clipped objective and a KL penalty to maintain model coherence. Alternatives to PPO include the reinforce algorithm, which models the entire sequence as a single action, and reinforce leave one out, RLO, which uses a multi-sample Monte Carlo estimate to reduce variance. In this section, we discuss the transition from PPO to reinforce in the context of reinforcement learning from human feedback, RLHF. PPO, an actor-critic algorithm, leverages lower variance estimators to improve learning, but this comes at the cost of introducing bias. This is not ideal for RLHF due to the strong initialization of the policy. Reinforce, on the other hand, uses an unbiased Monte Carlo estimator which can have high variance, especially in large action spaces like NLP. However, with a strong pre-trained model, this high variance is mitigated. We also explore the necessity of clipping in RLHF. Clipping is used to prevent large policy updates. but empirical evidence suggests it is rarely necessary in this setting. This supports the idea that the environment in RLHF is stable, and large off-policy updates are rare. In this experimental setup, the authors utilize two main datasets: the TLDR summarized dataset, which includes 116,000 human-written instructions and 93,000 human-annotated preference pairs, and the Anthropic HH dataset, which contains 112,000 training preference pairs. For the models, they employ Pythia 6.9b as the base model and conduct an ablation study using Llama 7b to assess the impact of the pre-trained model quality on learning from human preferences. A context length of 512 tokens is used during both supervised fine-tuning and reward model training. For evaluation, the authors measure optimization quality by reporting average rewards on 1,000 test samples and simulate win rates using GPT-4 as a proxy for human evaluation. Additionally, they assess the alignment tax by measuring fluency and diversity metrics. Figure 2 illustrates the test rewards across various training stages. Notably, RLO demonstrates superior performance over all other methods consistently. Conversely, vanilla PG consistently achieves higher test rewards compared to PPO. The reinforced method with a baseline, as referred to in the caption, employs a moving average reward baseline as described in Equation 8. Figure 3 illustrates the comparison of sample efficiency between RLO and RAFT across training with K values of 2 and 4. The plot demonstrates that RLO consistently outperforms RAFT given the same sampling budget. Notably, RLO with K equals 2 either matches or surpasses the performance of RAFT with K equals 4 on both datasets, using a Pythia base model. This indicates that RLO effectively utilizes all generated samples for better optimization, contrasting with RAFT, which only fine-tunes on the top-rank sample. In the context of reward optimization, RLO, reinforced with a baseline, and other methods consistently outperform vanilla PG and PPO. This is particularly notable because these methods do not model partial completions, suggesting that this approach may be unnecessary. Additionally, RLO demonstrates superior sampling efficiency by consistently outperforming RAFT with fewer samples. This is achieved by using all generated samples for optimization, unlike RAFT, which only uses the top-rank sample. Finally, in terms of simulated win rates, RLO achieves the highest scores, significantly outperforming PPO. Reinforced with a baseline also performs well, often on par with or better than vanilla PG, further supporting the argument against modeling partial completions. Table 1 showcases the final win rates on generations for held-out test prompts in the Anthropic HH and TLDR summarized datasets. The metrics are reported for the checkpoint with the highest test reward. Key points include RLO, K equals 4, achieving the highest win rates, reinforce outperforming vanilla PG, and RLO demonstrating greater sample efficiency than RAFT. Figure 4 illustrates the sample efficiency of RLO and RAFT by plotting their test rewards at various training stages based on the total number of samples seen, normalized by batch size. This figure highlights that RLO is more efficient in using online samples compared to RAFT, demonstrating this efficiency across different datasets and models. Table 2 presents language fluency and diversity metrics on the Anthropic HH dataset. Key points include RLO achieving the highest win rate with K equals 2 in the HH dataset, RLO being more sample efficient than RAFT, and the DPO model generating overly verbose text while PPO generates shorter text. These metrics help in understanding the performance and characteristics of different models in terms of language fluency and diversity. Figure 5 illustrates the sensitivity of RAFT and RLO to the KL weight during training. The left panel shows the training curve for R, X, Y, while the right panel displays the KL distance, DKL. With K equals 2, under higher KL weights, RAFT not only performs worse than RLO in optimizing reward but also deviates more from the reference policy. The curves are exponentially smooth to enhance readability. Figure 6 illustrates the impact of adding noise to training rewards at different levels, sigma equals 1.0, 3.0, 5.0. The results show that RAFT experiences a more pronounced drop in reward compared to RLO. This sensitivity of RAFT to noise is attributed to the addition of reward noise, which affects the relative rankings and thus the training reward. In contrast, RLHF demonstrates a more robust performance in optimizing rewards under noisy conditions. In this work, the authors argue that the reinforcement learning from human feedback (RLHF) setting provides a strong initial policy, which, when combined with prompt conditioning, addresses issues of high variance and large action spaces. Empirical results support this claim, showing that the vanilla policy gradient reinforced method outperforms proximal policy optimization (PPO) despite its high variance in traditional deep reinforcement learning settings. Additionally, the study revisits the modeling of learning from human preferences and demonstrates that the reinforce estimator, despite its simplicity, enables effective reward optimization. Finally, experiments indicate that RLHF, as a multi-sample extension of reinforce, outperforms RAFT, DPO, and PPO while maintaining robustness relative to iterative fine-tuning methods like RAFT. However, the limitations of the study are not extensively discussed, suggesting potential areas for future research and the need for further investigation. The study has several limitations. Firstly, the issue of reward model over-optimization, where the optimization trajectory of the proxy reward diverges from the goal reward objective, has not been studied. This is left for future research. Secondly, the exploration of the LLM baseline in a single token action framework, where partial sequences are modeled and intermediary rewards are provided, is limited. The study concludes that modeling partial sequences is unnecessary in the RLHF context where rewards are attributed only to full sequences. Lastly, the study is limited to simulated win rates from a large language model and does not measure correlation with final human evaluation preferences. Additionally, the study did not explore reinforcement learning training using other rewards such as Rouge, BLEU, or other metrics commonly used in natural language processing. In this section, the authors acknowledge several key individuals and groups for their contributions to the project. They thank Ivan Zhang, Phil Blunsum, and Florian Strub for their helpful discussions. Special thanks are extended to Matthew Geis for his multiple fruitful discussions on the framing of the work and feedback on the final manuscript. Additionally, the authors express gratitude to their colleagues at Cohere and Cohere for AI for their continued support throughout the project. Thank you for watching.